So this is a 5-day workshop. Actually, it's 5 2.5-hour periods. Conducting a workshop through Zoom is, especially on software, is a little bit challenging, we feel, because we personally conduct a lot of workshops and most of them are in person. But I think it's also provides us with a great opportunity to train the stakeholders and the scientists and others associated with DSSAT on at least exposing you a little bit to crop modeling in general, and specifically on spatial modeling using craft for in-season yield forecasting, as well as for climate change application. I really appreciate the opportunity provided by Glory and his team at AFRIGIST to facilitate this workshop. I think its capacity building and training is very important and plays a critical role within NASA's SERVIR program. So today, as you can see on the slide here, I will give you a brief introduction to crop modeling. I will talk a lot about DSSAT because that's the underlying crop model in the craft system. And then tomorrow and the rest of the week, Dr. Shelia will take it over and will emphasize the training on using craft. So I really would like to encourage you, if you have any questions, to interrupt me during my presentations. This is supposed to be informal. I know, again, this is challenging when we do this through Zoom. Please don't raise your hand, but just unmute and ask a question, and you can interrupt me. There are no dumb questions. If things are unclear for you, then please ask me. And then at the end of my presentation, again, I'll also provide you with some opportunity to ask some additional questions as well. So we all know that agriculture is an extremely risky business. I mean, farming is a risky business. Agriculture itself is associated with a lot of uncertainty and risk across the globe, not only in West Africa, but also in the US and many other countries. Farmers are affected by what we call the daily weather variability that varies from day to day, that varies from season to season, that vary across pace. And we especially know that extreme events in the form of droughts, floodings, temperature extreme can have a major impact on agricultural production. There are also uncertainties with respect to what we call the biotic stressors, pests and diseases, and even weeds that can affect agricultural production system. And ultimately, agriculture is not about the yield, but it's really about the costs and the economic returns, because farmers ultimately need to make a living with respect to being able to feed their family and make a major contribution to the globe. So we saw recently with the war in Ukraine, fertilizer prices skyrocketed because of the increases in energy prices, which has affected farmers across the globe. We also have issues as it relates to governmental policies. We have some cases price protections, trying to keep the prices low for the general population, but at the same time, this affects the agriculture producer. We have low prices. So farming is a risky business, and the underlying concept, what we're going to be working with today and the rest of the week, is we're going to work with computer models. So we're working with computer models. When we talk about agricultural system, we're looking at interaction with what we call the genotype, which are differences among the crops. We're looking at the environment. I already talked briefly about weather conditions, but it also relates to soil conditions, because soils are how the plant extracts water, how the plant extracts nutrients. And then the farmer manages his crop. Farmer, in some cases, has the option to plant a different crop, maybe plant a different variety. He can change his input depending on the financial resources he has access to. So there's some variability. So the question we're going to pose today is, can computer models help reduce uncertainty and risk as it relates to climate variability as well as climate change? Now, why are we using agriculture? So why are we using models in agriculture? So I'm not really sure about the background of some of you on the call. I've met several of you. Some of you are working in GIS. Some of you are working in data science. But if you look at the traditional agronomic approach, research approach, is that researchers in West Africa, in the US, and across the globe conduct trials. They conduct experiments, normally for 2 different years, where they might evaluate different management practices, such as the amount of fertilizer that is being applied, different varieties, different planting dates, maybe even comparing different crops, etc. So this has been really the traditional way of conducting research, but it is quite challenging, especially if we look at the varying environment we see across the globe. So trying to translate the information we obtain from field research and then applying that to an on-farm simulation source system has been quite challenging. So this is where we come in with what we call a systems approach, where we're trying to develop computer models that can predict growth, development, and yield as a function of weather conditions, etc., and base that on the outcomes of the experimental research that has been conducted. Now, when we're conducting experimental research, it's not just about publications. What we really want to do in the agricultural system is, first of all, we want to understand how a crop, a variety, when we're talking about cropping systems, responds to differences in input. And then we want to be able to predict that system with ultimately being able to control and manage. And again, as shown here on the slide, this is nothing new. It was already proposed by Henry Nicks in 1983, who was an Australian. And ultimately, what we really want to do is provide what we call adaptive management options to our stakeholders, so that we can ultimately look at risk reduction, improve the economic livelihoods from our smallholder farmers, and also look at environmental sustainability. So with these models, we can evaluate different management practices, and we get to that a little bit later on. And then we can do what-if studies and then provide these different options to farmers. So we're not using models in this case to tell a farmer what to do. It's up to the farmer to decide on which of these options he would like to implement, depending on how risk averse he is with respect to his management operations. So if we look at a systems approach, we can first of all do what we call research for understanding, and then we can start looking at what we call problem solving. So in basic research, we always develop a model. It might not necessarily be a mathematical model, it could even be a mental model. We have a hypothesis. Let's say, okay, we think something is different. We collect our data, and then we analyze our data. In some cases, with a very simple statistical analysis. We might even be using AI, or in our case, we're starting to look at dynamic crop simulation models. These models allow us to do a prediction. Then we might be collecting additional data to evaluate our predictions that hopefully will lead to a further increase in understanding, and that will then result in additional research. Because again, the agricultural system is extremely complex, and we never will be able to replace field research with either models or even with artificial intelligence. But then at the same time, we can use these models to look at what we refer to control, manage in a version of decision support, as I showed you in the previous slide. So we can take the same research model, implement it in a decision support system, and then look at applications and analysis that ultimately provide what we call actionable information to our stakeholders. So then you might pose the question when we talk about agricultural model, what is an agricultural model? And from the outsider, you might think that agriculture is just a single discipline, but if you look very carefully at the agricultural science, you might find people working on the impact of weather on agriculture, which we sometimes refer to as agrometeorology or agroclimatology. Some people looking at soil water flow, which are soil physics. Some are looking at the chemistry in the soil, so for the soil chemistry or fertility. We have plant breeders, we have people work on pests and diseases called plant pathologists and entomologists. So within the agricultural domain or discipline, there's a lot of different research going on. And traditionally, researchers are very much focused on their own sub-discipline within agriculture. They conduct research, etc., publish the data, and maybe some of that information can be used to provide information to farmers. But because of the complexity of the agricultural system, we really need to try to integrate the knowledge of these different disciplines and combine it in these mathematical models. And we're really trying to look at the state of the art of the scientific knowledge in the different disciplines, going from crop physiology to plant breeding to agronomy, soil physics, agrometeorology, etc., and even economics to provide actionable information to stakeholders. So first of all, it is about developing these models, but what it really is all about ultimately to provide advisory using science-based models through decision support systems. So farmers can improve production, can improve product quality, they can optimize resource use, and also reduce the environmental impact. For instance, here in the state of Florida, we have very sandy soils, we have tropical rains. Farmers do apply a lot of fertilizer because they want to maintain yields, but at the same time, because of the sandy soils and the rain, some of that water drains through the soil profile, taking nutrients with it, so we have a lot of pollution. So we're using the models not only at predicting yield, but also looking at best management practices. So there are a lot of different ways we can use these models. What we're really then ultimately looking at is understanding the different management options to provide what we call actionable information to our stakeholders. A little bit further in my presentation, I will show you some examples of what we really mean with that. So when we're looking at these models, really, these are the type of systems we're trying to understand. So what you see here is a rice plant, a flooded rice plant. I know that in some areas of West Africa, especially in Senegal, we have flooded rice production. And you can see on the screen, you see rectangles, you see circles, you see ellipses, etc. You see a lot of edges, arrows, etc., and connections. So for those of you familiar with plant physiology, we are looking at simulating a process that is called photosynthesis. It takes light, it takes water, it takes CO2, and it results in carbohydrates that we then partition to leaves, to stems, and to other plant components. We're looking at transpiration, water loss for the leaves, and we're looking at the same time at root water uptake. So within our models, we're trying to develop mathematical equations for all these processes here on the slide, and many other different processes. To look at the soil plant atmosphere continuing, look at the plant carbon balance, looking at the soil carbon balance, we're looking at the plant and soil nitrogen balance, and also looking at the plant and soil phosphorus balance. So moving from a generic approach, a little bit more about DSATs. So I refer to DSAT as what we call a crop modeling ecosystem. You can go to our DSAT portal, www.dsat.net, to obtain some additional information. And the DSAT crop modeling system is not new. It actually was initiated through a project that was funded by the United States Agency for International Development, USAID, from 1982 from 1993, to look at food security in developing countries. The project was called IPSNet, International Benchmark Sites Network for Agrotechnology Transfer. And the underlying idea again of this project was to look at a systems approach where we integrate the different disciplines within agricultural sciences, as I showed in my previous slides, combine it into crop models, and then evaluate these models and come up with different management strategies. So the initial models that were part of the DSSAT system are referred to as the series maize model, the series wheat model, the soy grow, and the peanut grow models, developed by various groups in the United States. And in order to work with these models, we had to develop what is called data standards. And for those of you already working a little bit with GIS, you know a lot of the tremendous amount of data that goes into these systems. Similar with crop models, if we're trying to predict yield, we need to provide the daily weather data as input. If you look at the soil conditions, we need to provide soil characterization as input into these models. We need to provide a little bit of information about genetics. And we'll also need to provide the management conditions. So we had to come up with data standards for compatibility of these models, etc. So the first version of DSSAT was released in 1986 as version 2.1. And over time, we've released new versions of DSSAT. And as of today, we're working with DSSAT version 4.8.2. In your version of Craft, because of some compatibility issues, you'll actually be using DSSAT version 4.7.5. But in reality, there's not really much difference between the versions. So the funded project by USAID was actually ended in 1993. At that time, the US government said we were not longer interested in supporting this activity. But because of the greater effort among the crop modeling community, those associated with DSSAT, we have been able to work and improve DSSAT over time, even without direct support from the US government. So most of it has been what we call a volunteer effort to really emphasize and improve the various components of DSSAT and add more crops to the system and many other various things. So in the early days of the EPSNet project and DSSAT, we actually used floppy diskettes, as you can see here on the top left, and we actually sold the software for $495. We moved from 5¼ inch diskettes to 3½ inch diskettes. Then we moved to CD-ROM, shown on the right. And somewhere over time, we no longer had access to actually charge for the software. So we decided to make the software completely open source using what is called 3-clause BSD license. So as of today, you can actually freely download the DSSAT software. And since we've made the DSSAT software free, there has been an exponential increase in the interest of DSSAT and the number of downloads, which I show you in the next slide. So earlier, I talked to you as referring to DSSAT as an ecosystem. So the reason I refer to it as an ecosystem, we really have, first of all, a large group of people who are working with DSSAT. We have people like yourself, we refer to as the crop model users, either for DSSAT or for the craft system. And because we have such a large community, we also have a group of DSSAT trainers, not only the people at the University of Florida, and other institutions, but also in other countries across the globe. About 2 years ago, I was part of an effort to train people in Ethiopia to become crop model trainers. And we do this on a regular basis. In addition, it's not only the University of Florida who is helping develop DSSAT, but we also have other people in different institutions in the US as well as across the globe. So we refer to these as crop model developer. So we really have an ecosystem of people working on using the DSSAT, training the DSSAT, and developing the DSSAT. In addition, we have increased the number of models for different crops in the modeling system. In my previous slide, I referred to 4 or 5 crops. As of today, we have more than 42 different crops in the DSSAT system. It ranges from food crops, feed crops, fiber crops, fuel, as well as vegetable crops. And we continue to increase the models we have in DSSAT as there's more interest across the globe. In order to work with the models, you need tools and utilities because you need to prepare the data. And I'll briefly show those to you following my presentation. We're basically preparing the input data as well as the utilities for analyzing the outcomes of the model. I briefly already referred to the minimum data for model run operation, here shown as model calibration and evaluation. So as a model user, it's extremely important that you first of all have to calibrate your model for local conditions which require data. And then you also have to evaluate your model with another set of data we refer to as an independent data for model evaluation. So as a person who works with DSAT, people always criticize us to say that we require too much data to run the model. But our response really is that we have defined this minimum data set to make sure that it can be easily collected by people who are working, conducting research in the field, and at the same time, when it is used as input for the crop models, can provide reasonable answers as well. So it's a very delicate balance. In association with that, we also have tried to develop a set of data standards we currently refer to as the CASA data standards, which hopefully will be implemented by other modelers as well. So if you have a data set for DSAT, might also be able to use it for other crop models, such as the EPSIM model developed by the Australians, or the WOFOS model developed by the Dutch, etc. And then last but not least is really the application programs within DSAT. Calibrating a model is interesting, evaluating the model is interesting, but what is really is important is these application programs. So this workshop will focus more on the spatial applications and using the craft shell for spatial applications for in-season yield forecasting, and also looking at some climate change applications. So as I mentioned in my previous slide, we have the DSAT ecosystem, here shown as the DSAT user community. So we've received close to 27,000 download requests since August 2017. On this slide, the number shows a little bit less, but it continues to increase over time. You can also see the distribution of the requests as of January of this year, where some of our main users are found in India, in China, the United States, and Pakistan. But we also have a significant user community in Africa, including West Africa as well. So we currently have had requests for at least 194 countries across the globe. And this continues to increase over time. So the DSAT software system itself is a shell, although people sometimes refer to DSAT as a model, but DSAT is a shell. And again, I will give you a demonstration once I complete my presentation to see how it functions. So within the DSAT shells, we have various tools for preparation of data. And then we also have the analysis program to look at single season analysis versus crop rotation analysis versus simple spatial analysis as well. So again, to emphasize the DSAT system, so this shows a schematic of the organization. So again, DSAT, the user interface is really a shell. So underneath the shell, we have our model, which we now refer to as the cropping system model, or CSM. We have to support the software as shown here on the left, prepare the weather data, the soil data, the experimental data, parameter estimation, etc. And then we have the application programs as shown here on the right for graphical analysis, for sensitivity analysis, seasonal analysis, and crop rotations. The other emphasis we have is data. So whenever we add a new crop model to the DSAT system, we provide to the users at least one example data set that had been used for model development, for model calibration, and for model evaluation. In the early days, we were using a database system, but we've come to the realization that database systems are not very efficient. So as of today, at least for DSAT, we're using our ASCII files as input. So if you have Notepad or Notepad++, you can easily open these files, modify them if you're familiar with the structure, and also look at some of the detailed inputs. Unfortunately, when we start working with spatial data, such as craft, ASCII files, again, are not very efficient. So Bogdan will introduce you a little bit more tomorrow and the day after tomorrow, how to upload and add data to the craft system. So then with respect to this cropping system model, this is currently developed in what we call a modular structure. I mentioned in a few slides ago that in the early days we had 4 or 5 different models for different crops. But we came to the realization early on, we were trying to model especially the soil processes and some of the weather processes. These are the same when we look at cereal crops, grain legumes, fiber crops, etc. So we decided to combine all these models into one large model, which we now refer to as the cropping system model, that allows us to share modules to simulate weather conditions, that allows us to share modules that deal with crop management, as shown here in green, for planting day decisions, for harvesting, for irrigation management, fertilizer application, residue placement, tillage, etc. For the soil plant atmosphere, calculation of potential ET, calculation of soil temperature, etc. And also for the soil conditions, looking at the soil water dynamics, looking at soil nitrogen, soil phosphorus, and organic matter. Where we see differences is actually in the plant modules. So with this modular structure, we have different plant modules, which I'll show in the next slide. But it also allows us in this modular structure to use what we call different approaches to simulate some of these processes. So because of data limitations in our models, we use what is called the Priestley-Taylor approach to calculate potential ET. This is solely based on air temperature and solar radiation. But some of you might be familiar with FAO 56 or Penman-Monteith. And this calculation requires wind speed, relative humidity, or very pressure deficit as input, which is not readily obtainable from many weather stations. But however, if you have that available, then you can use this alternate approach in the DSSAT model to calculate your potential ET. The same for the simulation of soil organic matter. We know, especially for low input systems, which are very common in West Africa, that we need to do a very good job in the simulation of the soil organic matter dynamics. So already about 15 years ago, we brought in a model called Sentry, which is quite well known for simulation of organic matter simulation, into DSSAT as a submodule, so we could do a better job with respect to the simulation of soil organic matter dynamics, soil organic nitrogen, and soil organic phosphorus. So for the plant modules, we have here maintained the different approaches. So here on the right, you might find the original model series maize, series sorghum, series millet, and series rice. Some of these models have been expanded. So on the series rice, you find a model we call series sweet corn, which was derived from the series maize model, and series sugar beet model, which was also derived from the series maize model. We've added other modules for substrate potato, a pineapple model, and many other ones. What you see on the left is what we call the crop grow template. So this was the original model that was first used for the simulation of soybeans, grain legumes, peanut, and dry bean. We came to the realization again that the physiology of these crops is very similar. So therefore, we're using a generic template for the simulation of photosynthesis, biomass partitioning, respiration, etc. for these crops. But then we use external data files to define a specific response to temperature, to photoperiod, plant composition, drought stress, etc., which are unique for soybeans, for peanut, for pigeon pea, for chickpea, etc. Over time, we have used the same template, crop grow template, to also address other crops, such as fiber crops. So we currently use the crop grow template for cotton. So you might be wondering, how can you take a peanut model and simulate cotton? And the only difference is nitrogen fixation. So we turn off the nitrogen fixation simulation when we actually call the cotton model. And then the external temperature responses, photoperiod response, etc., are handled through data files. So with respect to the details of the simulation within the cropping system model, So again, it requires inputs, as I mentioned earlier. So we use daily weather data. So the standard inputs are daily total rainfall, maximum and minimum temperature, and solar radiation. We simulate a one-dimensional soil profile. So we need to know the soil physical and chemical characteristics of each horizon or each layer. We need to know some information about the surface conditions, such as slope and color. Need to know some information about permeability and some other conditions as well. With respect to management, these need to be defined with as much detail as possible. So we need to know the planting date or transplanting date, depending on the crop. We need to know the spacing, plant density, and with respect to the inputs, we need to know the dates, the amounts, and the type of inputs. For instance, for fertilizer and for irrigation, we need to know the dates and amount. If residue is added, either manure from animals or crop residue from other crops, we need to know the composition of the manure. We need to know the dates and the amount that those are added. So these are all the inputs into the model, the standard management, weather and soil. And then we also have the genetics. In my previous slide, I referred to you to the crop grow template. So we have a whole set of inputs that relate to temperature response, photoperiod response, plant composition, drought stress response, CO2 response. So these are all genetic parameters at the crop level or species file. So these are inputs, and these are provided to you when you use the model. So you don't really have to change them. What is somewhat important is what we call the cultivar parameters or the variety parameters, because we know that in each country, different varieties of cultivars are being grown, and we also know that breeders release new varieties on a regular basis. We as DSSAT model developers are unable to really maintain a large database of the genetics. But this is where the responsibility of the user comes in, where he actually needs to calibrate a model based on some local observations before it can actually be used. So these are the inputs to the model. The model operates on a daily timestamp, because as you can see, we use daily weather as input. We normally start our simulations at planting, or in some cases, if we don't know initial conditions of the soil, we might even start our simulations prior to planting to simulate fallow conditions. So once the crop has been planted, every day the state of the systems is updated, and then we will predict emergence, we predict first leaf, we predict occurrence of flowering, first seed, and then ultimately physiological maturity and harvest maturity. In parallel, we were simulating photosynthesis, respiration, we simulate partitioning of biomass to the different plant component. During grain filling, we simulate biomass partitioning to grains. And then ultimately, when the model has predicted harvest maturity, we ultimately predict yield. But as I said earlier, this is not only about yield prediction. We can also look at resource use, shown here on the right yellow rectangle, so we can see how much inputs are required to grow a crop. So if a crop has to be irrigated, we can look at the minimum amount of water required to run the model. We can look at environmental impact. So we can look at pollution of nitrogen to the groundwater. And recently, we've also added greenhouse gas emission component to our model. So we can look at the effect of management conditions on NOx emissions and methane emissions as well. And then within the DSSAT system, not really within a model, but within the DSSAT system as a whole, we can also look at the economics. So we'll look at the production costs with respect to the cost of the inputs. We can look at the prices of the products. Could be yield, but it could also be the byproducts. If we look at a dual purpose crop, such as cowpea, where a farmer might harvest the grain, but use the fodder to feed the animals. That ultimately then allows us within the DSSAT shell to calculate net income. So again, to summarize, these models require inputs. So we need field and soil characteristics, daily weather data. We need to have information about the cultivar characteristics and management. So first of all, you need to prepare your input to run the model. You need to have some observations, such as yield, or maybe dates, phenology dates, flowering maturity, that allows us to calibrate a model for a local variety. Then we highly recommend that you also evaluate a model with what we call an independent data set. So that would be a data set that was not used for model evaluation. Then once you've done that, then you can conduct in silico experiments on your computer, which we refer to here as what-if experiments. So you can ask many different questions, and computer power is cheap, so you can really evaluate many different management scenarios. And ultimately, with the idea that you can provide excellent information for climate smart agriculture, really depending on the type of application you're interested in. And in a few slides, I'll show you some of the applications that these models have been used for. So again, the data is very critical for these simulations. So you cannot just download DSAT or even download Craft. You start running the system. Credibility of any modeling system is very important. So if you're going to make recommendation to your stakeholders, either smallholder farmers or your government, you really need to demonstrate that these models function properly for your conditions. So this is where experimental data play a critical role. So you can see here a field experiment shown here on the left, or even experiments conducted under controlled conditions. It might be more challenging for your situation in West Africa. But again, when we're looking at climate change, for instance, these growth chain conditions can be quite important to look at the response of a crop to high temperature or CO2, etc. So we really tell especially experimentalists who are concerned that crop models might take over research, that experimental data are needed. The same when people start talking about AI, although I'm personally not a big fan of AI. AI requires a lot of data. So AI is not going to replace experimental research because of the complexity of the agricultural system. So as an example of what these simulations look like, here you see a graph of an experiment, of a simulated experiment, comparing that to observed data that was conducted in 1978. So this is quite an old experiment, but again, the data doesn't really matter much. It was conducted here at the University of Florida in Gainesville, and this happens to be soybean. And on the x-axis, you can see day of year. Hopefully, most of you are familiar with the concept of day of year, where January 1 would be day of year 1, and December 31st will be day 365, except for like this year, when we have a leap year, it will be day 366. On the y-axis, the dry weight in kilograms per hectare. And you see 4 lines here. So this is an experiment that was conducted under irrigated conditions. But you can see that somewhere in the early part of the season, there was sufficient rainfall. So those the 2 lines on top of each other, the red line and the green line. But somewhere around day 235, 240, you can see that actually the drought started, so rainfall stopped. And you can see that there's a significant decrease actually in the green line due to the dry conditions. While for the irrigated conditions, you can see that the red line still continues to increase. You can also see with the blue line, which is the grain yield for irrigated conditions, versus the black line, which is the grain yield for rain-fed conditions. So the continuous line reflects what is done with the model. So again, the model operates on a daily time step. In some cases, it might actually be running on an hourly time step, using daily weather data as input, using crop management as input, and using local soil conditions. The symbols reflect observed data points. So in this case, a graduate student went into the field and every 7 days to 10 days harvested a meter of row, separated the leaves, the stems, the pods, and the seed from the plant, dried the individual components for 2 days, and then weighed the individual components. So that's what's shown here. So you can see that the model does do a very good job in predicting the observed data. But again, this is partially calibrated, so there's some tweaking that had been done with the coefficients. But again, even with the calibration, the model does a very good job. Some people sometimes ask is if we're doing curve fitting here. So again, these lines are not regression lines. These are based on dynamic simulation using tens of thousands of equations that operate on a daily time step. So to convince you a little bit more about the response of the model. So again, this is data from the United States, but we can do similar responses from other areas across the globe. So these are variety trials. Again, these are for soybeans. So across the globe, including in West Africa, when breeders release new varieties, they conduct variety trials at different locations and in different years to make sure that those varieties perform well, and they only release the best ones. So what you see here on the left is the response of soybean for yield on the y-axis against rainfall on the x-axis, and rainfall is shown here as the average amount per day. Normally we show seasonal total, but we decided to turn this around. And you can see that somewhere around 3 millimeters to 3.5 millimeters per day, the soybean crop doesn't show any response any further to an increase in rainfall. So each point represents here a particular location and a particular year for that variety. So left is observed, and on the right you see what we simulated with the model. So we were able to obtain daily weather data for all those locations, soil characteristics, especially water holding characteristics, and management. And you can see that the model does do a very good job in simulating the same response as you see on the left for the observed data. So we did the same for temperature. So on the left, you see the response to maximum temperature. So actually, soybean is a crop that doesn't like very high maximum temperatures. So you can see in general that the higher the maximum temperature, the lower the yield. And again, we use the same inputs from those locations into the crop model from the previous slide, and you can see that the model is able to predict this very, very, very well. So then when we look at the applications of the DSSAT crop modeling systems, so in the early days, we really were using DSSAT for yield gap analysis, looking at analyzing low yield, especially developing countries, and try to see what type of interventions were needed to increase yield. We can also extend that yield gap analysis to what we call precision agriculture, which has become very prominent in Europe, in the United States, in Australia, and many other countries, where actually within the field, farmers might have a combine, and it shows the variability within a field with respect to yield. So this then can be used to prescribe what we call variable management to make sure that we can address this spatial yield variability within the field properly. The models can be used for irrigation management, so we can actually, through automatic scheduling, determine how much water would be required to actually increase yield. And at the same time, we can use water use projections to see how much water will be required in the future for irrigated agriculture. And then we can determine if maybe we can decrease the amount of water required for those situations. You can look at soil fertility management, especially as it relates to nitrogen management, but also recently we've added phosphorus to the system too. We can look at plant breeding applications, G/E interactions. So again, more and more this has been common as well, especially if we have variable environments. We evaluate the initial breeding lines for a few locations, and then we can use the model to look at the performance for other locations for which we don't have any experimental data available from yield trials. And then we can look at yield prediction for crop management. Of course, for climate change applications, these models have been used quite extensively. We can look at climate change, not only looking at the impact, but they can also then ask the next question, what type of adaptation practices are needed to maintain the same type of yield level. We can also look at mitigation. So are there ways that we can reduce the greenhouse gas emission from our management practices? We can look at climate variability and climate uncertainty. We can look at in-season yield forecasting, and this will be, I think, part of your exercises during this week, working with craft. You look at soil carbon sequestration. So again, agricultural system can actually sequester carbon, so the models will predict that. We look at targeting aid with early warning system. We look at land use change analysis, environmental impact. Somewhat controversial, but we know that agriculture, in many cases, the agricultural crops are also being used for biofuel production. Although this might affect food security, from a farmer's perspective, it is ultimately about the income he received from selling his crop. So in Europe and the US, corn is used extensively for ethanol production. In Brazil, sugarcane is being used. In other countries, again, various crops are used for biofuel production. And then risk assurance. I know this has been some evaluations of providing risk insurance to smallholder farmers. And again, the models can play a key role in that as well. So to show you a little bit more about the overall impact of the DSSAT modeling system, about 2 years ago, I had a visiting scientist from India who actually did a meta-analysis on the use of the DSSAT system in South Asia and China. And he found that a total of 205 papers were published in about a 12-year period. And then he worked very hard to extract the information out of these papers. So what you see here is the performance of 3 of our models within the DSSAT system: the wheat model, the rice model, and the maize model. On the top 3 panels, you see the response of these models in the prediction of flowering and phases and maturity. And you can see that we see a very high R-squared for those predictions for the wheat model, the rice model, and the maize model. On the bottom 3 panels, we see the prediction for above ground biomass as well as yield. The blue dots are yield, grain yield, and the red dots are biomass. And then again, the R-squares are quite high, maybe slightly less than the prediction of the days. So we see here that the models being used by many people in this region can do a very good job in predicting yield for various cereal crops, including wheat, rice, and maize. So I want to show you 3 different types of applications of the DSSAT system. I want to start with one for the southeastern United States. So the question posed here is, why should farmers actually care about the climate? Because mainly we talk more about weather and not necessarily about climate. So what you see here is a map of the southeastern United States. It includes 3 states: the state of Alabama, the state of Georgia, and the state of Florida, where we are based. On the left, you see the difference between total average yield and neutral years, residuals. So you see some counties, so these are political districts that are red. You see some that are yellow and some that are green. So in neutral years, when we talk about ENSO phases, there is not really a clear signal with respect to response of corn yield. Then when you go to the center map, you see a lot of red, very dark red counties. So during El Nino years, again, part of the ENSO cycle, there's a very strong signal that results in a decrease in yield for corn production. And then you see on the right, green and dark green. So these are positive residuals, meaning that there's actually a positive impact of La Nina years on corn yield. As you know, hopefully, the ENSO phases, El Nino and La Nina, are basically predictable because we can look at the temperature of the Pacific Ocean around the equator. So, and across the globe, this has a different impact across different regions. So El Nino, as shown here, might be dry and warm in one area, could be wet in another area. And because we can measure the temperature of the Pacific Ocean, we can actually, and there's a delay in the actual impact of the temperature Pacific Ocean across the globe, this becomes predictable. So in this slide, you can see the La Nina phases. Again, it's slightly different. There's some cool areas, actually. In West Africa now, we see some dry. In East Africa, we see some wet and cool in South Africa. Again, you see different responses across the globe. So this is really predictable. So that means we can provide advisories to the farmers. So how can we use models for that? So what we did in this particular case is already an older study. We conducted simulations, in this case, for the peanut crop, and there could be any other crop as well, in the counties where peanut is a dominant crop. So you see here the green highlighted counties. So those are the counties we selected. We evaluated different planting dates. So the question was really, what would be the optimum planting date for growing peanuts in those counties? And we compared rain-fed versus irrigated conditions. We used long-term historical weather data from each of these counties. In some cases, we had 38 years. In other cases, we had 107 years. And then for each county, we used three representative soil profiles. So we conducted a tremendous amount of simulations for these counties. And then this resulted in these types of box and whisker plots. So hopefully you're somewhat familiar with the box and whisker plots. So because we have long-term weather, each individual weather year results in one yield prediction. We have different planting dates, and we have the answer phases with respect to El Nino and La Nina. So here you see a comparison for rain-fed conditions, irrigated conditions on the bottom for La Nina conditions, and for rain-fed and irrigated for El Nino in the top. So for La Nina on the rain-fed conditions, which is the left panel, the median yield you can see slowly decreases over time. So the later the planting, the lower the yield. Well, for irrigated conditions, yield is fairly stable. But in all cases, we see a tremendous amount of variability, as we would expect. For rain-fed El Nino conditions, we see a slight increase potentially in the median yield, but again, a tremendous amount of variability, as you can see with the large box and whisker plots, and the extremes with the circles as well. And then El Nino conditions is somewhat stable. Now, this is a chart which you would publish in a scientific paper, but this is something that is very difficult to show to a farmer, because he really doesn't know what to do with it. So we try to translate this information into something that is useful. So first of all, we did some additional optimization routines, also bringing in economics. So what you see here is for one location, in this case, for Camilla, Georgia, looking at maize for El Nino years, using about 44 years of historical weather data from 1951 to 1995. A 3D graph where we have planting date on the x-axis, fertilizer rate on the y-axis, and profit on the z-axis. So there's a particular region actually that is optimum with respect to when a farmer should plant his crop and how much fertilizer he should apply with respect to the profits. And again, this is an older graph because the economics today don't really apply to 1995, but it's just an example of how we can conduct these simulations, also bringing in the economics. And then to translate this information to do something useful, we actually developed a web interface, which is called agroclimate.org. So what you see here is a seasonal forecast that comes out of the United States NOAA office. So this is the equivalent of the National Weather Service umbrella organization. So this is a slightly older slide, which I grabbed in early January with respect to the seasonal temperature outlook on the left and the seasonal precipitation outlook on the right. And in that case, for Florida, which is in the right bottom, we see an above chance of an increase in precipitation, and temperature would be near normal. So on this same website, we also implemented a graphical interface to look at these yield distributions I showed you from my previous box and whisker plots. So we talked extensively to extension agents, which are very common here in the States. So these are the people who provide information to farmers. We also talked to consultants, and we also talked to other organizations. And the farmers were not really interested in yield predictions. They more or less knew what the yield levels were for the individual field. And we also didn't really trust the actual yield predictions for the model for each individual field. So the farmers are much more interested in looking at what they call probability distributions. So farmers understand risk very well, and understand the risk of net returns. So what you see here on the right is the comparison of different planting dates, May 15, May 29, and June 12, and the amount of returns in dollars per acre. So in general, it's likely that if a farmer plants later, there's a slightly different distribution with respect to the returns compared to an early planting date. So here, then the farmer can decide with respect to how much risk he's willing to take. Is he going to plant his crop on May 15? Is he going to plant his crop on May 29? Or is he going to plant his crop on June the 12th? So it might be likely that May 15 in this case, because he has the best probability distribution on the higher amounts in a dollar per acre, might be the best decision for these particular conditions for this particular county. So what you see in the left top, and a farmer can basically look at a pull down window or an extension agent. He can select his crop. He can select his type of variety. In this case, we also look at the state of Georgia, which is a very well-known state for growing peanuts. He can select his county, so political district, and then he can select his soil type, in this case shown as Orangeburg, loamy sand, and he can pick 3 different planting days. And then he knows there's going to be El Nino, so he has selected El Nino for this particular year. So this is an example of how we can take very complex situations, complex simulations, dealing with complex situations, summarizes information in an external database, which you can store in the cloud, and then readily provide this information to the stakeholders who then decide which type of management strategy they want to implement. So again, we're using lots of what-if questions, but it's ultimately up to the stakeholder to decide what to do. We provide him with different options. We don't really tell him in this graph how he should plant his crop. Now the next one is going to be an example of craft. So this is the tool you'll be working with. So in this case, I've shown you an example of a state in Ethiopia, Oromia State, where we worked with the Department of Agriculture to try to provide in-season yield forecasting for maize. Ethiopia is a very large country in Africa. It has challenges growing sufficient food. So the Ministry of Agriculture is very interested to know if during the current growing season, farmers can produce sufficient food, or if there's going to be a drought and the government should actually invest in importing food. So Dr. Shelia will explain a lot more about these simulations, but again, if we go from point-based simulation that I showed you in my previous slides to these spatial applications, we now need to look at spatial weather data as inputs for each individual grid, because we're simulating this on a grid, as shown on the right. For each individual grid, we need to have soil profile information, and here we're using the AFRIGIST-SERVIR database. We need to know information about fertilizer distribution in this particular state, and we need to know which maize varieties are being grown. And in addition, we also need to know where the crop is actually grown. So we cannot assume that each of the grids we have 100% maize, because we know that the actual total amount of maize production varies from farmer to farmer, and not all the grids are 100% agricultural production. So we then conducted these in-season yield forecasts. So this is for the 2020 growing season, and we see here 3 different forecast dates. So basically, and Dr. Schillier will explain this in more detailed, we use the current weather data up to yesterday, in this case, say March 30th, as input into the CRAFT system. And then we provide a forecast on March 31st for the remainder of the growing season. So we repeat this on April 30th. We replace the weather data that we now have available until April 30th, and then conduct a forecast. And the same for May 31st. So you see the spatial variability of yield across the state here, with the purplish blue colors, the higher yielding areas, and the orange part, the lower yielding areas. And you can see some slight changes in the distribution of the yield across space. So this information was evaluated with some observations, and again, hopefully Dr. Schillier will tell you more about how these evaluations will be conducted in CRAFT. We found in general that the model performed well, or the CRAFT system performed well for high yielding areas, but that we're a little bit challenged by the lower yielding areas, because again, these models are not perfect. They don't simulate all the soil conditions, and also not able to simulate all the biotic stresses and the abiotic stressors. And then finally, I want to show you another example for West Africa. This was a study conducted by the ACAI project, which was headed by IITA in collaboration with CEAT, with emphasis on Cassava, and really looking at trying to come up with recommendation to increase cassava production in Nigeria, as well as in Tanzania. In this case, the cassava model of DSSAT was used, and the underlying question really was, what is the best planting date for cassava in Nigeria, and what is the best harvest date? Farmers get paid not for the total amount of cassava weight, but actually of the starch content. And as you know, the starch content might vary depending on when the farmer harvests his crop, and also when he actually plants his crop. So in this particular case, we use the DSSAT model for each individual grid, again, as shown here on the right bottom, for the cassava production region in Nigeria. And we evaluated 52 different planting dates. So we planted cassava in the model every 7 days. We use long-term historical weather data, so that's why you see the box and whisker plots in the top left panel. And then we also evaluated different harvest months. So we harvested at month 10, so after 10 months, all the way up to 15 months. So cassava is, as you know, a very long season crop that could be in the field all the way for more than a year. So again, determining what is the best planting date and what is the best harvest date is very critical. So all these simulations were conducted on our high-performance computer, what we call the Hypergator, because again, it's impossible to do these types of simulations on a personal computer. And this information was stored in a very large database, and then as part of the ACAI project, some tools were developed on a smartphone, as well as some other devices, to provide this information to the stakeholders using NGOs, using extension, etc. And again, these are all pre-run, so all the farmer had to do, or the extension worker has to do, is find the location of a particular field and then retrieve the information from the external database. So then finally, I want to talk a little bit about overall DSSAT approach. So because we have a very large user community, We spend a lot of time in capacity building and training, so I'm very excited to see that AFRIGIST has facilitated the training on craft using Zoom today and this week. In the crop models itself, we rarely do the online training. We really prefer to do this in person. So we've organized workshops at the University of Georgia, so not the University of Florida, but at the University of Georgia, since early 2000s. We already advertised our next workshop, which will be held on May 25th this year. You see here some group pictures, early on 2002, where we had 33 participants, all the way up to last year, 2023, when we had 58 participants. Apologies. In addition, as I said, the DSAT development is community activity. So we have the DSAT sprints or hackathons, where we come together as a group once every 6 months. We do that in a hybrid format, using both in-person meetings as well as through Zoom. Excuse me for a minute. So in addition, we have our portal. So not some of you might be familiar with this. DSAT.net. So if you want to download Craft or if you want to download DSAT, this is where you need to complete the forms. Dr. Shealy has provided you with Craft through a Google site that we request that you still register for the software later on. We also have recently added some YouTube channels, so you can look at some of the basic parts on how to work with DSAT. And we update this website on a regular basis to show new developments in DSAT training, etc. So I do want to emphasize that these models are not perfect. I mean, there's some limitations to what we can model, especially because the agricultural system is so complex. So we do a very good job in what we call modeling potential production. So there is no limitation to the agricultural system. We can do a good job in predicting water, simulating water limited production, nitrogen limited production. We're currently starting to look at phosphorus and potassium. We're starting to look at pest limited production, but this is really very challenging because each individual crop has a different set of pests and diseases, and not for all pests and diseases actual models are available. There's still a challenge with looking at intercropping. Economics, of course, is another component. I showed you some very simple parts of DSAT on how we can deal with economics, but in the real world, economic complexity, there's much more, such as labor costs and investments, etc. We're slowly starting to look also at what we call food quality, not what the outside product looks like, but really the internal quality. So what is the percent oil, what is the percent protein in some of the products that we can simulate, because that has become more important in the recent days as well. So it's not only about predicting and simulating food quantity, but also food quality. And last but not least is really the human decisions. This is very challenging. For those of you who work with farmers, each farmer makes a different decision. And that's really impossible to simulate. So that's one of the main reasons that in the models, when we apply the models, as I showed you in some of the examples, we emphasize the different options. So a stakeholder, a farmer, can decide what he wants to do, depending if he's risk tolerant or if he's risk averse. So then with respect to the crop models, fact or fiction, I think these models can do a very good job. I mean, I've been working with models for most of my career. We do need to realize it's a mathematical representation of a real world system. which is a very challenging system. We do emphasize that these models require careful evaluation for local conditions. And also, and especially when you start working with your spatial data, they do require accurate input data. So you need to be very much aware of the limitation of some of your input data and take that into consideration when you look at your model simulations. So once you've conducted the evaluation, these models can be used quite extensively to look at not only yield prediction, they can also be interested in looking at resource use and look at environment impact, nitrogen pollution or greenhouse gas emissions. You can look at the economic returns, and they really are a very nice tool to explore what we call what if type question, conducting in silico experiments on the computer to evaluate different management decisions and different management options. It can also be a nice tool to look at research design and analysis. There are many gaps in science, so we can then use the model to see, okay, what should you emphasize the next field research experiment, so we can use that information to help improve the model or help evaluate the model. We've also found that many people use DSSAT as a teaching tool, both in undergraduate classes and graduate classes across the globe. In some cases, when we receive requests, we suddenly might get a request of 20 or further requests in one day for one particular country. As a professor instructor has recommended to the students to download the software. And then, of course, these models can be used for policy and planning. I showed you one example from Ethiopia, but in many other ways, these models can be used as well. So again, the agricultural system is challenging, and this is somewhat of a visionary approach where we should be heading. I noticed several people here in the training were associated with the Met offices. So good weather predictions, good climate predictions play a critical role in this whole modeling aspect. I've only talked about crop prediction, but I understand that many of your farming systems also include livestock. So in some cases, the byproduct of the crops is being used for animal feed, or the manure of the livestock is used as input for fertilizer for the crops. So we really need to go even beyond just crop prediction, but also look at livestock prediction, pest and disease prediction, etc. So we can provide actionable information to our stakeholders, producers, and policymakers. So with that, I'll be glad to answer any questions. It seems like you guys are a very shy community because none of you so far has asked any questions or has interrupted me. So I'll take another sip of water, and hopefully there will be some questions or there's some discussions about these things. So thank you.